Hello, this exercise I'm calling the Iowa exercise. I got this from the Iowa Stormwater Management Manual. And Iowa Stormwater Management Manual, and specifically this is in the uh, in Chapter 3, Stormwater Hydrology. There's you can see the general hydrology goes through here. There's a section, low impact LID hydrology. And it has a couple examples in there. And I thought these were good examples. This is actually based on the Prince George County, Maryland guidance documents, but I thought Iowa did a good job on it. So this is specifically to look at the hydrology using some different LID technologies. The example we're not going to talk specifically about which LID BMPs. What we're going to do is go through again. Here it's we have a site, and we're going to determine the volume need to be treated for volume control. We've done that. Peak control, we've done that. But also, as in this idea of coming up with certain volume that needs to be treated by BMPs for water quality. Recently, here nearby in Harrisburg, Pennsylvania, one of our student project teams is working with an organization that has a drainage issue, and they designed a rain garden and stuff, but the main objective or the main constraint for their design was that it had to be designed for water quality. So there's guidance out there on how to size various BMPs that will improve water quality. Rarely, I can't think of an example, but maybe never, but rarely anyway, does water quality get measured. But well, it get measured as the developer has to measure water quality. Usually, it is if they go through some procedures where they can show that they're using a technology that improves water quality, that will work. So we're going to go through this back to the hydrology. There's a process in there, and this is included in the handout. So you have a handout that I was showing earlier, and then also I'll make available the section of Chapter 3 of the Iowa guidance document. You can Google it and find the whole thing real quickly, but I'll include that on there if you want to grab that. So the idea here is that, first of all, we calculate the existing curve number and proposed curve number, and then calculate the time of concentration. And the objective is to make the time of concentration greater than using LID than it was without it. So if we can prove that the time concentration is greater, then we can move on. We're not really going to spend any time on that in this example. We're going to focus on the sizing of it for volume, peak, and water quality. So it goes through there, and then we select these are volumes, volume for water quality, volume water for storage, or peak, and we go through that process and select the BMPs. This process is also shown. They have another table that I also have in the handout that just shows how you go through it step by step. So we're going to go through this example. Again, this is a example. It's not the process used for everything. No, it's in Iowa you're supposed to use this, but so we'll go through this. I'll switch back to the example and we'll start walking through it here. So what we have in our example is a 28-acre site. After development, there'll be 7.84 acres, that's 28%, 7.84 acres of impervious surface. And we're going to go through their procedure to calculate the volume needs to be held or treated for volume control, water quality, and peak control. So the first thing we have to do is determine the curve numbers. The pre-development curve number, the area is naturally meadow. Recently worked on one site with the students where the municipality says, and I guess it's pretty common, you should use meadow for undeveloped areas. So that it might be specified what type of land use that you use for the undeveloped or pre-development area. So then the curve number is that 70 from we calculate from 70% of soil group B and 30% of soil group C. And if I look in the numbers for the meadows there, for meadow it's C it's 58, and those B it's 58, C it's 71. So if we go down here, it's 0.7 times 58 plus 0.3 times 71, and so that's a 61.9, or a curve number of 62. We're going to call that curve number of pre, which in the guidance document they refer to that as previous, no, pervious, and then we're going to calculate the curve number after development. Now, after development, we said all we know is we have 28% impervious, and in the terminology of the Iowa document, they call that P sub IMP as 28. So for any impervious surface, if you look up here, remember the curve number is 98. It doesn't matter what kind of soil it's on top of. If it's impervious, we have a curve number of 98. So then the composite curve number after development we can calculate as, well, we had a 62 for undeveloped, 70%, 72% is still undeveloped. So we have the 62 of that's undeveloped. We still have 72% of our site is that. And then we have now 28% of our site is impervious. So the weighted of the curve number for that comes out to about 72. So that's going to be our curve number after development. But the Prince George County and then Iowa, they've adopted, they give us some credit if we disconnect those impervious areas. For example, if we have water running off a roof and we run it then across a lawn before it gets anywhere else where we can have the sheet flow, then we can get credit for that. So we can actually reduce our curve number. So the equation they use to get credit for that is this here, where we have the, so before development, we had 62. And then after development, we're going to increase that. This equation here is just what, equation here is what I did there, except with a little bit of algebra and then added this term here where I get some credit for the disconnection. So I have 62 there plus the impervious. I have 72% impervious. And just on the algebra on this, we then get the 98 minus the 62. And then we can reduce that number. So this number would give us the 72, right? Yeah. And then we multiply this times 1.1 minus 0.5 times the disconnected. Oh, and I didn't give you that number. So I'm going to say disconnecting 75% of my pave or my impervious. 75% is disconnected. So then I get my credit looks like this, 1 minus 0.5 times R is 0.75 times 5. A little messy there. R is the ratio. The guidance diagram is a little confusing because they like to use percentages as whole numbers like 28, but then this one they use the ratio. So 75% is disconnected, which gives us a ratio of R of 0.5. And then this was 62, and then percent impervious was 28. And then they also 20%. I maybe should have made up my own example, but they have a 28-acre site, and then 28% of that is impervious. Anyway, if you can keep the numbers straight, what this does is this now reduces the 72 down to 68. So because we disconnected those impervious areas, so we could have instead of a parking lot, we could have smaller parking areas and the water runs through a lawn or something in between there. We disconnect those, we can lower it from 72 down to 68. So that's what we're going to do is we had our pre 62. Just from the impervious area, we'd get a 72 for the post, but because of the disconnection, we get a credit. And we get 68 for our post. So we've calculated our curve number. Our next step in the process is to calculate the time of concentration. We're not going to spend time on that. Just from the example, we'll say that our curve number, and again, if you scroll down through this document, I have the flow chart there that you can calculate the time of concentration before and after. Go back up to this document again. And you try to lower the time of concentration. And this chart in the guidance document gives you some ideas of the different technologies, and you want to increase the time of concentration. I think did I say lower? I meant increase. More time means less runoff. So development decreases the time of concentration, makes it run off faster. So we want to add stuff in there that increases the time of concentration. So if we increase sheet flow, increase the flow path, flatten the slope, we can get increase the time of concentration, which is what we want. So back to our example, we can calculate the time of concentration. So this is the next step. We're not going to do this, and we're going to say, okay, in our example development, we put in some best management practices and we increase the time of concentration, and we're good to go. All right, the next step, we have to determine the design storm event that we're going to use to calculate our runoff. And the guidance document tells us that the design rain is the 1.5 times the initial abstraction. So we get that, and we've done this in class several times now, but we get the S is 0.2, well, initial abstraction is 0.2 times S, 0.2 times 1,000 over 62 minus 10, and that turns out to be 1.22 inches. So we're going to design our system to handle 1.22 inches. And what the method does is it gives us, okay, with that, wait, we didn't quite get there, did we? Sorry, 1.5, it's 1.5 times 0.2s. 0.2s is 1.22, 1.5 times, sorry about that, 1.22 is 1.83 inches rather. So okay, that's our design rainfall. So the method, if we go down here, gives us some graphs. Storage required to maintain pre-development runoff volume. So what I have here, I have proposed runoff curve number. And I'm paging to my document here, make sure I don't. For 2-inch rainfall, wait, I thought we had 1.83. In the example in the guidance document, it says 1.83 is close enough to 2. Use the graph for the 2-inch rainfall. So our existing curve number is 62. That's the pre-development. Our post-development was, well, no, not 72, because of the disconnecting adjustment. We can drop it down to 68, and we connect those. Go up this line there. Draw a perfectly straight line. Any perfectly straight line this way. And we hit right about there. So storage volume required to maintain pre-development runoff volume, hundredths of an inch. An inch isn't a volume. It's okay. That's the thing we do with the runoff with the NRCS method. We talk about inches of rain as a volume. So I'm going to say this is 0.11 inches. So in other words, we have to, according to this method, that's the amount that we have to store to make up the difference between the pre-development 62 curve number and the post-development 68 curve number. So this is the number we've been getting at before. This is a little different way to get at it. So back up here, zoom a little bit here. So this is from the graph, you get 0.11 inches. And that's for the volume control calculation. Well, what do we do with that? Well, before we go on and do our other, see what we need to control for peak or for water quality, let's look at what we're going to do with this. All right, so we have to store the equivalent of 0.11 inches over the whole site. For 28 acres, we have to collect 0.11 inch. That equals 3.08 acre inches. Divide that by 12, that gets 0.26 acre feet. So we have to store 0.26 acre feet of water. Where do we store it? Well, we can look up for our best management practices, and some of those, they give us a depth of the best management practice, integrated. So IMP is integrated. MPs, integrated management practices. So it says that this rain garden or whatever it is, it'll store 6 inches of water. So we can have, which is about 60 times that 0.11, 50 times that. So we don't have to have our MP or IMP in this case cover the whole site. We have to have it to get to store 3.08 acre inches divided by 6 inches. we need a half acre, 0.51 acres of the IMP. So that's the area of the IMP we need. And if we looked at that, we took that 28 acres times 0.11 inches 6, we can get the same number there. Just a little different way to do it with algebra. Now, if we use best management practices or integrated management practices that only store 4 inches of water, then that number changes. We need a little bit bigger. So 3.08 divided by 4 inches, we get 0.77 acres of IMP. Or, oops, be a 4 there. We said we calculated we need 0.51 acres of IMPs, and we if we're using 6 inches, if we use 4 inches, it needs to be a little bit bigger. How much bigger? Well, 6 over 4 bigger, 0.77. Actually, I'll come back to that. All right, so area drained to IMPs. What does that mean? Okay, so I got to collect 0.11 inches for the whole site. It comes down to if my IMP is 6 inches, I need to have a half acre. My best management practice needs to be a half acre. But how much of my area do I need to drain? So if I have one, and I can divide this up, but let's say I have one rain garden that's going to be a half acre. That's a big rain garden. Usually they're so little. So how much of my area do I need to drain into that rain garden in order to accomplish that? So I don't need to have this whole site drain into the rain garden. I have 1.3 inches of my design storm. So I need to collect 3.08 acre inches. Acre inches divided by inches, that gives me acres. So that gives me 1.68 acres drained. So if I can have 1.6 acres of my site drain into that IMP, I can accomplish my goal of storing that water. And I said one, so I could break this up into a number of pieces. Or another way to look at that is if I have, so I can take the rain that lands on the rain garden, so 0.51 acres of my rain garden, and it looks like if I need 1.68, I can have 1.17 acres in addition. Do you follow that? So what it's saying is that you're collecting 0.11 inches for the whole site, but you can take a part of your site and grab the water off of that part of that site and accomplish your volume goal for that. And probably we're going to have several pieces there, but you can't, the whole site doesn't necessarily drain to the same spot. And so you don't have to capture water from every part of the site. You just need to make sure for the whole site you capture enough water. And there are, they have a number in there that says about 10% gets lost to infiltration evaporation, or I guess not lost, it gets used. So if we can justify that, we can say of our 0.51 acres, well, if we're going to lose 10% of that, we only have to capture 90%, and so we can use a IMP that's 90% of the 0.51 acres or 0.46 acres. So that's just some sizing of this. And if you think through this, it'll make sense just doing the volume balances on where the water is going, make sure you collect enough. So let's go on to what they have in the guidance document as example 2, where they look at the water quality. So this is on the same site. Again, it's 28 acres. The new development will be 7.84 acres impervious. And the water quality treatment volume. So there's guidelines on how much volume of water you need to run through some integrated management practice that will treat the water. And this one doesn't really have say which ones are used for water quality. So they have a guidance in there that the RV, what's RV? Volumetric runoff coefficient. Okay, so water quality treatment volume is calculated by multiplying the 90th percentile annual rainfall event by the volumetric runoff coefficient and the site area. And this is from the document. Actually, this reference, I should double check that. That was for the old guidance document. They've updated it since I first made this example, and I've tried to make things match the new one, but I'm not sure that's the right reference. Anyway, so this is the formula they use for the runoff coefficient. Interesting, this 0.009 times I is the percent impervious color, so it's cover, so it's 28, not 0.28, it's 28. So it's the runoff coefficient 0.05, so 5% is going to run off, plus some more depending on how much is impervious. Use 0.009 times 28, and that gives us 0.30. And that 28 again is the percent impervious, not the area of the site. That's confusing. They have two 28s in there. Anyway, so for Iowa, the 90% cumulative frequency annual rainfall event is 1.25 inches. That's in the document. So the water quality volume you need to collect to treat the water quality. We're going to compare this to the volume we calculated earlier for volume control. We're going to use whichever one's biggest. So if the 90% cumulative frequency annual rainfall event is 1.25 inches, then the volume that we need to collect for water quality is that 0% runoff coefficient times 1.25 is 0.375 inches. What we have for volume, we had 0.11. Okay, so that's actually, so the water we need to collect for water quality is greater. So we can use the greater one of these. So a BMP to our IMP to hold the volume might also be used for water quality. If it doesn't get any, remove any volume, then we might have to add them together. But generally, and I think if I go to the document, I could have stayed actually in the one we had. Select higher values of volume Q or volume R. What's volume Q? The quality control is volume Q. The volume control, maintain existing curve number. That is, in other words, volume control. That's volume R. So generally, we compare the two and use the bigger one. Although you could argue if there's a one for water quality that does not also remove volume, maybe you treat that a little bit differently. But we're going to go with that. So it's 0.375 inches. That's greater than the 0.11 inches for the volume. So if we put all this together, the RV times the P90, which is 1.25, 0.3 times the P90 is 1.25 times the area over 12. So to calculate the volume needed, we have the RV, that's the runoff coefficient of 0.30 times 1.25 inches, that's our P90, times 28 acres. Divide that, that gives me acre inches, divide that by 12, that gives me 0.875 acre feet. So again, the water quality volume, 0.375 inches, is greater, higher than the 0.11 need for volume. So we need to go with the water quality volume to calculate our IMP area. So, oh, do we have to go through that all again? Well, no, we came up with 0.46 acres of IMP. That's when we accounted for, we had 0.51, then we counted for 10% evaporation filtration. So we had 0.46 for volume, but it turns out our water quality one is more than three times as high. So I'll just quick go 0.375 over 1.75 acres of the IMP. And then I can go back and calculate again how much of my area I need to run onto that IMP in order to capture that. It'd just be, what was our number up here? Was 1.6 acres drained. So I'm going to need 6 acres drained times 0.375 over 0.1, whatever that turns out to be. So I'm going to need to capture from a bigger area because I have to treat a bigger volume. There's another number in there. Calculate the volume required for peak discharge mitigation. So if I go down on this next graph here, it says storage volume for peak control, again for hundredths of an inch. And we do the same thing we did before. Our existing was 62. Our proposed was 68 after we do the adjustment for disconnection. And then we come over here. And doesn't that look the same? This is 0.11. This one might be a little more on. I could say 0.11 or I can say 0.1. So that's another graph it gives me for calculating, and I'm going to say 0.10. Might be 0.11. Very similar to the one for volume, and but still the greater number is the water quality volume. So that's the one that guides what we do. All right, let me just sum this up by showing again the step-by-step graph. Determine storage volume required to maintain runoff volume or curve number. Again, that's very much, or is it the same thing as our volume control we did before? Volume for water quality volume requirement. So it gives us another guideline for that. Then we choose whichever one is greater, and then also now we look at the peak. We use the second graph for the peak, and then we might have to size it for the peak runoff, and then if we need additional detention storage, we can go through there. We can use detention, we can use those IMPs and come up with something to take care of that water. All right, so that's the Iowa example. I want to show you a little different way of looking at it and introduce the idea of calculating a volume for treating water quality, and then also introduce you to the process. All right, that's it for this one. Thank you.